is from ISC Bangalore in 2024. He was awarded the prestigious PMRF Research Fellow in 2020 to support his doctoral studies. He is currently a senior scientist at the Science and Technology Organization, G Healthcare in Bangalore. His research focuses on applying artificial intelligence to both upstream and downstream tasks in medical imaging. So I hope the participants will definitely enjoy the session. Definitely there will be lots of query that sir will address during the session. So those who have not joined, I request you all to kindly join. Uh, so now I will uh, hand over the session to Dr. Naveen. So over to you, sir.
Yeah. So, yeah, thank you for the kind introduction. So, I hope I am clearly audible and you can
Yes,
see
yes,
me.
sir.
My visual is also on. So, in case I feel a drop in the internet, I will switch off my video so that we can have a smooth
Definitely,
session. Right?
definitely,
Yeah.
definitely.
So, I'll start sharing my screen. Please, if one of you
Mhm.
can
Yes, sir.
inform.
You must.
I think it's asking me to log off and log in. Just give me a minute. Some permission from my end. I'll rejoin.
Okay, no issue, sir.
Yeah. Is my screen visible? Can one of you please confirm?
It is loading. I hope.
Okay. So I have a yes from one of the participants.
Now the screen is visible. Yes, now it's visible.
Okay. All right. So let's get started with our discussion in the coming 30-40 minutes, right? So I'll try to present one of the works that we have done at Medical Imaging Group, part of Computational and Data Science Department at IISc Bangalore. So this is one of my PhD works, wherein broadly we have designed and developed a robust model to identify retinal disorders from optical coherence tomography images. Right. So a brief set of acknowledgements. So I have listed down my advisor, Professor Fanindra Elaverty, and all my co-authors, along with funding and different institutes that had supported my work and my stay at the IISc Bangalore. All right. So this is the paper that I'll be talking about. I mean, we're going to the details in the upcoming slides also. But briefly, right, so what we have done is that we addressed three critical challenges that we often face when we talk about AI-driven medical image analysis, right? So, of course, in this talk, we'll be focusing on deep learning or AI-driven image analysis on OCT. But typically, when we talk about any AI-driven application for solving image analysis problem. So there are three challenges, right? So the computation or the performance across different data sets and how well we can handle different out of the domain data when it comes into the testing phase during the inference time, right? So these are the brief contributions. But anyway, we'll be talking in brief about them in the upcoming slides. Right. So when we talk about DL-driven medical image analysis, right? So whatever any medical image that we see, let it be an MR image or a CT image or an OCT, so it has got a sequence of steps that are being involved. So briefly, we can list down these steps as a part of the flow diagram as shown on the screen here. It all starts with an acquisition, so wherein we have an hardware setup where the data is acquired, right? So when I say the data is being acquired, so for MR, we often simulate a magnetic field and then try to recover the MR image from the input that has been given. Similarly, for CT, X-ray, and all, we provide some radiation, and then we detect the amount of radiation that has passed through the given anatomy, and then we reconstruct. When I say reconstruction, some mathematical model depending on the modality. So for MR, we have a different forward problem, and then for CT, we have a different problem. For OCT or ultrasound, right? So we have different relations between the data that is being measured and the image that we are going to see. So there are two things here, right? So first we measure something. From that measurements, we actually reconstruct the data. So that is where the reconstruction algorithms come into the picture. And then once the reconstruction is done, we have nice images that can be processed or visualized or analyzed for further diagnosis, right? So on these images is what we do image-based tasks. So when I say image-based tasks, so typically, I hope the audience might have already explored some of the existing applications across different modalities. But briefly, if you want me to put in different image-based tasks that we can do on medical images, is like briefly we can classify them into one of the categories depending on the kind of task that we are dealing with it. And then we can segment out or classify each and every pixel or voxel that is present in a given image. And then, of course, the reconstruction, right? So reconstruction is an upstream task. So it tries to improve the quality of the image that we are trying to reconstruct, right? So there also AI or deep learning driven methods have been quite popular and they did well. And then one more interesting application that people came up with it is image translation. So when I say image translation, for example, if I have an MR image with me, can I get corresponding CT image out of it, right? So there are good set of applications for this kind of translation as well. And anyway, a super resolution is one more aspect. So wherein given a low resolution image, how well we can generate a high resolution image out of it. So briefly, these are some of the well-known or broad spectrum of image-based tasks, I would say, that AI has improved or performed well, or in some cases on par with an expert, right? So that is where we are currently in. So once this is done, then the last block we have the reporting, wherein the analysis of the diagnosis that came out of this particular image-based task is being reported and being sent out in the loop, right, to carry out further treatment or something. So briefly, to put in one slide, like what does AI-driven applications look like in a clinical workflow is what we have just discussed now. But given this, right, so when we talk about any particular task that we want to solve, there are certain challenges, right? So when I say challenges, especially in terms of AI-driven medical image analysis, so these are the three things that I would call upon as the major challenges to perform or to develop any deep learning based medical image analysis method, right? So the first one, if we talk about the data, so data availability, right? So getting access to medical databases is not that straightforward, right? So there are so many steps that are needs to be considered if you want to approach a hospital, then talk to them, set up an MOU, and then explain the problem that you're trying to solve. If at all they are willing to share it, then only it is being shared with us. But there is otherwise there is lots and lots of data that is available with different hospitals or different multi-specialty centers, right? So availability of the data is the prime challenge, especially for medical image analysis. Because natural imaging, right? So natural imaging, you can see, you can compare the standard open repositories that are there. For example, when you talk about computer vision tasks, right? So you compare with how many such repositories are there for the medical imaging on the same node, right? There is a good amount of difference between the amount of data that is available, right? But these days we are often seeing different challenges being coming out, and people are willing to curate the data sources and make it available publicly to different people who are working in the domain is really appreciated, right? So we all should aim for that aspect in the beginning, right? So if you have some time and if you have some efforts, if you can put in, making the data availability in the front end will automatically will lead to developing more and more robust models, I would say, when we try to solve any particular problem, right? So data availability is one thing. The second thing is variability in imaging protocols and scanners. Correct. So, for example, if you pick up any MR scanner or any CT scanner, right? So there are several options that you can provide when you are trying to image a particular organ given an anatomy, right? So there can be several things, right? The same slice coming out of the same MR volume from the same subject can look very different depending on the settings the scanner is being used. For example, in some hospital, people might prefer 1.5 Tesla, or in some hospitals, people might prefer 3 Tesla, right? So there is a good amount of difference between the excitation itself. And and not only this, but there are other factors which will influence, like for example, the resolution of the images might be different from the pixel spacing or the voxel spacing might be different. So given a particular and in particular modality of interest, there are several options that can lead to variability in the content or the perceptual quality of the image that we are going to look at it, right, while for the final processing. When we talk about ultrasound, that is even more what to say, like, so it is even more susceptible to this variability, right? So ultrasound is a freehand probe. So there is a probe and the expert is asked to usually they move their hand along with the probe on the organ they are trying to image. Correct. So that's the, I mean, like coming out at a wide scan plane itself is going to vary across the expert, right? So that is going to bring in another dimension into the variability of the images that we can observe. The third one is computational resources, correct? So right now, there is a good amount of work that is being carried forward in context of building lightweight models so that we need not depend on these heavy computational resources, which are very hard to buy. I mean, for example, if you talk about 96 gigabytes NVIDIA graphic cards, right? So RTX 9000 and all. I mean, 3 years back, that machine was costing around 11 lakhs. But right now, it might have even gone up, but it's not that easy to have such a huge amount of money to buy these resources at all times. Correct, but we can see, right? So these days, even the Google Colab or some other resources like Kaggle and all, they are also coming up with their own hardware wherein they are providing access to these computational resources given a time point. So given these three conditions, right? So whenever we try to develop any AI-driven solution for the given task at hand, especially for medical image analysis, we need to have a watch on these three things, right? So how much of data we have and what kind of variability we are going to expect from different data sources that we are going to process, and what is it that going to happen during inference, and how much compute we have to run, train, or infer all these models. Right. So with that motivation of the overall workflow of AI-driven medical image analysis, followed by the kind of challenges that we can anticipate when we think about deep learning or AI-driven medical image analysis. So we'll try to focus on one modality and a small classification problem. So before going into the details of the classification problem that we'll be looking at it, so let us try to understand a few things about optical coherence tomography. So OCT, briefly known as optical coherence tomography, it is a kind of cross-sectional imaging that can help us to view 2D and three-dimensional images of retinal layers. Right. So I will show you a diagram that will make things even more clear, like what cross section I am referring to and all. And briefly speaking, there are two variants of OCT. So one is called as time domain OCT, and the other one is called as frequency domain OCT. In frequency domain, again, there are two subcategories. So the first one is called spectral domain optical coherence tomography, and the second one is called swept source optical coherence tomography. So in this talk, the problem that we are going to solve now, we'll be using SDOCT images, which are spectral domain OCT images. So this is a small overview that will let us know, we'll try to understand the difference between time domain OCT and the frequency domain OCT. Right, but looking at these two images, we might feel that they look more or less the same, but there is a small difference between both of them. So typically any OCT system, right? So it has a broadband light source. So there is a beam splitter. There is a scanning or reference mirror. So this reference mirror is movable, right? So its position can be adjusted in time domain. But whereas in frequency domain, this is fixed at a given particular position, depending on the acquisition parameter. And then there is a photodetector here, and this is the sample where this is the sample that we would like to image. So during acquisition, what happens is that this broadband light source will emit a light, and this light is allowed to fall on the beam splitter. And from this point, the light is allowed to follow two paths. So one towards the reference mirror, and the other towards the sample. When the light hits this reference mirror and the sample, it gets reflected back. So the reflected light is, whatever light that constructively interferes at this beam splitter, so that is sent to the photodetector. And this photodetector will convert the light that is coming into it into the respective signal form, and thereon there are 3-4 steps that will lead us to the image. So similar setup you will see in the frequency domain OCT, but only the difference is that so the reference mirror is fixed here, but instead of a photodetector, there is a diffraction grating. Right. So if you remember in the time domain system, I told that the position of this reference mirror can be adjusted. So the main role of adjusting this reference mirror position is to make the light coming from different depths within the sample to interfere constructively. So if you change the position of this light, if this reference mirror, the light from different depths of this sample will constructively interfere at this beam splitter, and that is what is sent into the photodetector. So what depth you want to image, or the point or the depth at which we are imaging, is highly dependent on this position of this reference mirror. But whereas in frequency domain, this reference mirror is fixed at a given point, right? But what happens is that since at any given point of time, the light is being reflected from different depths. So the light coming from different depths is actually forms as a function of the wavelength of that particular light. So that particular wavelength, different wavelengths coming out of this beam splitter are allowed to fall on the diffraction grating, and this diffraction grating will separate out or spectral out the components of different wavelengths of this light. And interestingly, here the wavelength and the depth at which the imaging or the signal is being reflected back, they form a Fourier pair. So typically you take a inverse Fourier transform of the signal that you are being recording at the output of diffraction grating will actually form the voltage signal, right? So that is the small difference or the key difference between time domain OCT and the frequency domain OCT. So to put it shortly, so frequency domain OCT is fast because we are resolving the image information at in a single shot. We can image or we can resolve the information coming from different depths because it's just a transformation. But whereas in time domain, we have to move this reference mirror up and bottom depending on this particular flow diagram here, but it is slightly time consuming, and resolution wise also frequency domain OCT is what is better. So this is a 3D structure of an eye here you can see there are two scans. So one is called as an A scan, other one is called as a B scan. So if you look at the image, so A scan is typically one line present in the B scan, right? So one vertical line or vertical pixels in a given column in a B scan. So this A scan is what I was talking about, that we first image one A scan, and when we move the light source to fall at different columns of this XY plane is when we recover a B scan out of it. So typically, an optical coherence tomography B scan is actually a cross section of this particular 3D structure that is being shown on this particular slide, right? So now I hope you have an idea, like what is it that I'm talking about when I say that this is an OCT, this is a brightness scan of the given 3D structure of an eye or the retinal layers. So given this context on like how does an OCT image come out of a given hardware and all, right? So these are the common retinal abnormalities that are studied in the literature, right? So specifically, there are three different varieties. So the first one is called choroidal neovascularization. The second one is called diabetic macular edema. The third one is drusen. And in the last column, you see what is referred to as a normal or a healthy B scan. So typically, the visually appealing characteristics that are used to diagnose these three conditions is what being highlighted in the second row of this particular image, right? So for choroidal neovascularization, it's abbreviated as CNV, they are, I mean, the expert, right? The ophthalmologist usually look for a small subretinal fluid right above this retinal boundary, and some cyst-like structures at the retinal boundaries you see. So that condition is called as diabetic macular edema, and irregular retinal boundaries, right? So that is what which characterize this condition called as drusen. So these are the three visually appealing conditions that are often examined if we want to diagnose one of these three conditions given an OCT-B scan. Correct. So given this information of the data and the different conditions that are being often analyzed to predict such retinal abnormalities, like people in the research community, they have came up with different methods to perform the task at hand, right? So what is the task at hand? So given an retinal B scan, what we want to do is that we want to group or we want to classify the given B scan into one of the three conditions that what we have seen. Correct. So starting from conventional machine learning methods like Bayes classifier, you can talk about logistic regressions or support vector machines, or random forest classifiers, even multi-layer perceptron, and finally convolution neural networks. Right? All these methods they have been applied in one or the other way on a given input B scan to arrive at a given prediction. So when I say prediction, one of the class, either choroidal neovascularization or diabetic macular edema or what they call this drusen condition. But we all know, but looking at the advancements that have happened, right? So in this deep learning era, so we all agree, at least right now, saying that we have some hold on the performance being on par with the being performed on par with the experts as of now, which is coming out of these CNNs, right? So CNNs have become quite popular, and then even the medical imaging community have adapted them and they have designed task-specific solution, and they are doing reasonably well, I would say. But what is the problem, right? So as we have discussed earlier, so I told you that one of the challenge that we often see is that because of variability in the image acquisition, right? So from device to device, the hardware characteristics might change, or the operator who is using the device might choose some other parameters to acquire the image, and then different manufacturers might have what you call different ways to provide the initial input acquisition, in this case light, and they might be using different wavelengths, for example, in context of OCT. So all these things will account to some variation And when you compare images coming from two different data centers or two different scanners, or two people being two experts are imaging the same person but with different set of input parameters and all, right? So that is one critical challenge when we talk about AI-driven medical image analysis. So specifically, when we talk about optical coherence tomography, right, the signal to noise ratio of the B scans is varying with respect to different imaging protocols or different scanners or different experts imaging the same subject and all, right? So we understood that like noise level or the signal to noise ratio of a given B scan is varying with different OCT devices or acquisition protocols and all, right? So as a result, so what was happening is that, for example, we trained a classifier model from the data obtained from a particular hospital, and then we did some cross validation. We validated it. We found that the accuracy was close to 90%, or I would say some 92%, for example. But when you evaluate the same model for the same task, but this time on the data coming from a different center or a different device, the accuracy was dropping down to 75 or 80 in some cases. So we want to understand like why is it this happening, and what the main aim of taking up this project is to, so can we think of some solution specific to OCT imaging that we can provide as an additional input during the training process, so that we could control the model predictions, so that we do equally good even when the data is coming from some other center or some other device like that. So the challenge was that signal to noise ratio was varying. So that is what is making the model to have a consistent prediction irrespective of the noise level. So what can be the potential solution, right? So can we train these deep learning models to provide a consistent prediction irrespective of the noise level of the input B scan? So this is what we want to happen during the inference time, right? So irrespective of the noise level, I mean, when I say irrespective of the noise level, irrespective of the scanner or the different data center from which the inference test point or the test image is coming in. So we want to have a consistent prediction. So we want to predict CNV irrespective of what is the noise level or whatever the noise level be on the given input B scan. So what we thought was that, so can we enforce such a constraint during the training itself? So will that help the model to learn better so that it can provide robust prediction during the inference times? So that as simple as that. So that was what came into in our mind, that can this be a potential solution? So that can we train deep models in a way that we want to include such a constraint so that we do well during the inference time irrespective of the noise level. So that is where we move on, and what we call our approach is called noise regularized self-distribution. Okay, so before going into all these technical details, right, so let us try to understand what exactly this particular block diagram is trying to tell. So there is an input image, then there is an input B scan, let us call it as X, and there is a deep model F, and this deep model have a set of parameters called theta. So what we are doing, we want to give this image as an input to this model F, and we are arriving at four predictions, right? Four probabilities basically. So CNV stands for choroidal neovascularization, DME is for diabetic macular edema, DRU is for drusen, and NRM stands for normal. So the model is going to give you some predictions. So during training, since we know the ground truth, right? So we have expert annotations. So for example, this particular image, drusen being the correct class. So it's an one hot representation here. So what we do conventionally is that we minimize the cross entropy loss, and then you back propagate these gradients. And then depending on the gradient strength, we usually update these model parameters. So that is how a typical training of a CNN looks like for a classification problem at hand. So what we do is that along with this, we also have another realization of this particular input denoted as f of x. When I say f of x, so f of x is the noisy counterpart of this input image x. So then we repeat the same process We also send this noisy image as an input into this deep model F, and this is going to give us some more predictions. And on these predictions also, we want to ensure that we want to minimize the cross entropy loss, even on the predictions coming from the noisy counterpart of your input X as well. So this is what, so here you can see LC1 stands for cross entropy loss 1, and this is cross entropy loss 2. So these two together is what formulate the LCE here, right? So overall loss you can see here. So this is what LCE actually stands for LCE1 plus LCE2. But if you notice, there is another term called LSD. So SD stands for self distillation. So what we do is we want to enforce another regularizing term as in the view of a regular kind of a regularization. So what we want to do is that we want to ensure that the predictions on the given input X and the predictions on the corresponding counterpart of X should also lie close to each other. So not only that, we want to move both these predictions to the expert predictions rightly, but also we want to ensure that they themselves also should be close to each other. But there are here two terms. So one is LSD1, other one is LSD2. So these two terms actually guide each other's predictions, right? So for example, in LSD1, the predictions coming out of on the original input image X will actually behave as the ground truth, and for that particular term, the predictions on the noisy counterpart as the variable parameter. So for LSD2, the predictions coming out of f of x will act as a ground truth, and the predictions coming out of coming from the original image x will actually be the variable parameter which we want to adjust it. So this way, this is a two-way constraint wherein we are trying to enforce that the predictions from these deep models, irrespective of the noise levels present in the corresponding input B scans, should lie close to each other. Right. So this kind of two-way distillation is not new. This has been evaluated for two or three computer vision tasks. So wherein here we adapt it to the OCT imaging, right? So when I say we adapt it to the OCT, because so this particular noisy counterpart, right? So it can be anything, but for particular for this OCT imaging, so noisy counterparts with low SNR levels was doing good compared to other variants of it. So to put it more terms, right? So anyway, these are standard loss functions for cross entropy as well as the distillation, right? So for both the self distillation and all, we actually minimize the KL divergence between both the predictions, right? So one prediction coming out of your original input, and the other prediction is coming from the noisy counterpart of it. So that is wherein we minimize these terms, and then we back propagate the entire loss and we tune the model parameters. So I'll come back to the aberration studies in the end. So wherein we try different combinations. Of course, there will be so many questions like how did you arrive at this, and why not you do distill only one way, or why are you distilling both the ways, or like what will happen if you switch off one of the cross entropy and all. I mean, we did sequence of experiments one after another to understand the importance or the requirement of four different subcomponents of the original loss function, right? So we will look at that. So some details on the data sets that we have used. So there are three data sets. One is from University of California, San Diego, and one is from Duke University, and the other one is from Noor Eye Hospital in Iran, right? So we have how many patients are there and different conditions, CNV, AMD. So AMD is like age-related macular degeneration, and then we have diabetic macular edema, and then recent and normal, right? So these numbers are the 2D images, right? So when we do experiments and all, we made sure that the data is separated at the patient level, so that we are not mixing different B scans from the same patient on both validation, training, testing, right? So everything is separated at patient level. Correct. So now I will spend some 5-10 minutes on different experiments that we did, and then we'll talk about limitations and what are open challenges still that exist with respect to the task at hand. So what? So first, what we did is that we picked up three architectures. So I'll call them as ResNet 18, MobileNet V2, and ShuffleNet V2. So why did we choose them? Because they are well-known lightweight methods that are quite popular in the computer vision or deep learning literature, which are known to perform on par with their heavyweight counterparts. Right. So for this way, the baselines that we have chosen are at least they are directly addressing the issue of computation. Right. So we can run this MobileNet V2, especially and ShuffleNet V2 on handheld devices, and they often run at a good speed. So these are the three baselines, ResNet 18, MobileNet V2, and ShuffleNet V2. But if you see, there is something called as ResNet 18 plus noise, NV2 plus noise, and SV2 plus noise. Right. So what does these methods represent? Right. So these methods actually represent. So if you look at our proposed methodology, we are explicitly ensuring a consistency in the model predictions, irrespective of the noise level. But we are often know that adding noise to your input and then training the models is also a one way to bring out a kind of L2 regularization, which is going to be implicit, right? Of course, there has to be certain assumptions to nicely derive and show that adding noise to your input image is a kind of L2 regularization that you are doing on your weights, right? So there is a good amount of nice explanation for that. So we also picked up that as an experiment, just to try to understand and compare how does explicitly ensuring the consistency is going to perform when we compare with this kind of implicit way of adding noise, which also will act as a kind of regularization. So for every baseline method, there are three methods here. So ResNet R18 is the original ResNet 18 model. R18 plus noise is actually the ResNet 18 model itself, trained with input being added with some noise as a kind of an augmentation. And then you have R18 plus NRSD. So NRSD stands for the proposed method, which we call it as noise regularized self-distillation. So for all the three baseline methods, so we have all the two variants, right? One is original baseline and the noisy counterpart experiment. So this is coming to the methods, right? So the metric that we are showing here is of course the F1 score, which combines both precision and recall. And then in the first row, if you see, there are different numbers, right? So 0. 0.1, 0. 0.4, 0. 0.7, 1.0, 1.3, and all. So these are the noise levels that we have added to the testing data during the inference time. So of course, this noise is what we are adding, and then we are evaluating for an experimental sake just to understand whether the model is behaving as expected or not, right? So for that, we have did this experiment. But the first column, if you see, it is an original B scan, right? So without any artificial noise being added. So you see, like all the methods, they often perform equally good on the original B scan, that whatever we are trying to infer here. But as the noise level increases, right? Of course, this is a synthetic experiment that we have done, but we can see a nice pattern. The F1 score of the baseline models is being falling, right? So it's going from 0.9 to 0.67, 0.57, 45, 38, 33, 29, and 27. As the noise level is increasing, the F1 score or the performance is dropping. But when you look at the singular experiment wherein we are adding noise during the training itself, which we call it as R18 plus noise and all, so that is also deteriorating, but not at the pace at which the original baseline model was going down, right? So, for example, if you look at this particular experiment here, the ResNet 18 model dropped down to 0.45 at a noise level of 1.0. But the corresponding R18 plus noise experiment, wherein we add noise to the input and then train the model, it is doing as 0.77. But wherein in the proposed method, wherein we are explicitly ensuring a consistency in the prediction, was doing comparatively better, I would say, to the R18 plus noise model. And this trend was consistently observed across different baseline methods. right? So this way, the main purpose of doing such a synthetic experiment, I would say, because we are artificially adding something to understand, like, okay, we made an attempt to make the model understand few things. So is it doing in that way or not when we are actually inferring it? But this is a synthetic experiment, right? Because we are adding the noise level. So to really evaluate the model in the context of completely out of domain, wherein the noise levels are changing in the real time environment. So what we did is that, so we trained again similar set of models on 60% of the data from NEH database, and we evaluate it on remaining 20% of the NEH database. And we also evaluate the similar same set of models on the complete DHU database, right? So wherein here the DHU database, the last three columns which we are seeing in this table, they are completely out of domain in the context of training or validation or something, right? So these two databases have a good amount of variation in their acquisition parameters or in their noise levels or the way the image quality appears. So there is a good amount of difference there. So here, when again, when you compare all the three methods across three different baselines on the NEH database, they reasonably do good, around zero point 0.9 or 0.91, I would say, all the methods. There is no consistency. I mean, there is a good amount of consistency among them because the training data was from the same database, wherein the 60% of the data which we have used to train, and then we evaluated it on the remaining 20%, right? Only 20 or 30%. The performance was more or less good across different methods because they have seen these characteristics during the process of training. But when we evaluate them on again a new set of data coming from the Duke University, so there we can see the difference, right? So, for example, the precision or the F1, which were in the range of zero point 0.9 when the both training and testing sets were from the similar site, they have fallen to 0.79 and 0.67. Correct. So this is because the variability in the scan parameters or the variability in the image quality, right? So that is what we were keep on iterating starting from the presentation. This is a big a challenge that we need to consider. But I don't say that like we have been doing as good as when both the training and testing data were from the same side, but we were reasonably better compared to other two baseline experiments that we took up. Correct. So and again, the similar pattern from MV2, I mean, MobileNet V2 and the ShuffleNet V2 as well, right? So kind of. And then we swap the experiment. So wherein this time we train the models on the DHU and then we evaluate it on NEH in the other way around. So here also, I mean, like we also whatever we try to ensure, it also got deteriorated, right? So we are also falling from 0.93 to 0.66 or 0.61 in the context of F1 score and all. But again, reasonably better, correct? So this may not be of diagnostic quality, but there is a lot amount of work or more generalizability needs to be brought into the picture. But we with this experiment we understood that like there is a little bit of a scope definitely wherein we can make the model understand like what it needs to look for when it want to put these images into three or four different bins, right, given the task at hand. And then we also compare with existing methods in the literature, right? We compare them across how many parameters are there in these models, what is the size and the amount of flops that are required to perform one inference, what is the inference time on CPU, GPU. And we also compare across both the data sets, right? So the first 5 to 8 columns from precision to AUC, they are on the NEH side experiment, and the last four rows are on the DHU experiment that we have seen in the previous slide. So this is an interesting experiment that we did. So wherein we had access to some 30 B scans, where for each of the scan we have a low SNR scan and we also have a corresponding high SNR scan. So the first row is a condition of A and B, and in the second row we have a normal B scans. So you see some bounding boxes. So those bounding boxes were used to compute the signal to noise ratio in the respective images. And since we know the ground truth, a kind of ground truth, I would say, so we also report what is the PSNR and what is the corresponding SSI in between the low SNR pair, I mean low SNR image versus a high SNR image. There are small tabular columns beneath every image, so where you can see all the three methods that what we have been talking about in the previous slides and all. But along with this, you can see some numbers, right? So these numbers are actually the softmax probabilities. So these numbers are actually the softmax probabilities. If this probability is in red color, so it indicates that the model made a wrong prediction. So it could not predict AMD as a AMD condition. So it is a wrong prediction. Wherever you see a red color probability, that is a wrong prediction. But all the remaining probabilities reported in black font, they are actually the correct prediction. So here what we are trying to understand is like we are trying to understand the variation in the confidence of these models when we have a real-time low SNR scan being provided as an input and corresponding high SNR scan being provided as an input. So we felt that, I mean, I'll show you a more compact tabular form. So wherein we saw that the standard deviation of the confidence of the proposed approach was minimal, right? So it's a kind of an indicative nature saying that we are not oscillating because of the explicit regularization that we have used to tune the parameters of the model, right, during the training process. So that is, I mean, this is one good experiment, I would say, which gave us some belief saying that we are not actually oscillating given the model prediction, right? And this was also being observed during the first synthetic experiment result that I have shown, right? So where we were adding noise at different levels to understand like what exactly is going to happen to the model predictions. And again, right? So I hope all our participants know these class activation maps. They are quite popular in the vision literature, of course, in medical imaging as well. So wherein we are trying to identify or project back the gradients and try to understand what regions in the given image have actually led to the corresponding prediction. So again, here we have three different conditions. So one is CNV, choroidal neovascularization, diabetic macular edema, and drusen. And column wise, you have three noise levels. And in every set of images, the first row is from the implicit noise experiment, which is R18 plus noise. You add noise to the input image during the training itself. And in the correspond and in the same set, in the second row, we have the proposed method. So here, what we are, and these numbers actually represent the what is the confidence of the model in predicting it. So here what we have seen is that, so irrespective of the noise level, whatever activation maps we have projected back, so they are trying to look out for similar regions in the given input image, right? So for example, you look at this Jusum case here. In the last row, you have the confidence probabilities, and you can see the heat map is always trying to look for a similar structure, irrespective of the noise that has been added to the input image during the process of training. I mean, R18 plus noise, the implicit way to impose regularization by adding noise to your input image and train it, even that was also doing reasonably good. But in one or two cases, for example, in the DME case, right? So here it was moving out of the ROI, right? So there is nothing, just a speckle over there, and somehow it is trying to highlight these pixels, saying that they also have contributed to your model prediction, which is false, right? So for a reason or a DME, you have to look for the similar cystic related pixels or voxels in the given input OCTD scan. And this was the appellation that I was talking when I was explaining the proposed method and why did we choose four different variations. And again, right, so we switch off one and we study what yields effect. And so like that, after a series of experiments, so we felt like having all four of them is what is of the interest, right? So that is wherein we are going to achieve the best out of the model when we are trying to predict it. What are the limitations? So the proposed method could not handle. I mean, we evaluated it. The B scans coming from swept source OCT, right? So remember, I told that whatever OCT B scans that we have seen or we have used or experimented in this particular studies, they come from spectral domain OCT. So what we did, we took the same set of models and we evaluated them on SSOCT, which is swept source OCT. So to give you a small context, so in swept source OCT, the light, the wavelength of the light is being slided across a given spectrum, so that you are sending light pulses of different wavelengths and you are simultaneously trying to recover the depth information. So, if you remember in SDOCT, the imaging information at a different depth will come out as a function of the wavelength, but in SSOCT, it will come out as a function of time. And so SSOCT is way faster compared to SDOCT and all. It has got the capability to image at even more depths compared to SDOCT, but it brings in a different noise into the context, and which is what our models have not seen during the training. Hence, they were unable to perform the same task with a given reasonable performance. Right. So, but anyway, they were whatever we proposed, they were doing not great, but they were slightly better when compared to the other baseline experiment that we had done with a significant margin. I would put it that way. But still, a lot of work that needs to be done. And always, I mean, like what I have learned is that so whenever we are thinking about bringing a new deep learning model or new AI-driven workflow for a given task, especially focusing on medical image analysis, so if we can think about what we can bring in as an explicit content which actually fits into the challenge these modalities can offer, right? So in this case, the noise or the SNR level of the images was of our prime interest. So what we did, right? So we tried to have a consistent prediction irrespective of that noise level. So that way, if we can think about modality-specific solutions along with the task-specific solutions, I think we have a better chance to solve more problems at a fundamental level, right? So even here, we are just simply applying an existing deep models to the task at hand, and then we are getting some predictions. We are recording some accuracies, and we are publishing some papers, promoting the research and all, but if we can still further investigate, right? So still, if you ask me, there's a lot of work that needs to be done because I could clearly see the model, whatever we have experimented, they could not handle this same classification task from the images coming from SSOCT. So how do we handle it, right? So again, there are so many techniques that are being popped out from different dimensions of the research community, one coming from pure ML perspective, some theoretical guarantees, and some these conferences like CVPR, ICML, ICLR, Murex, and also so many new techniques are being coming out of it. But how we can adapt them explicitly to our modality or our task at hand is going to be an interesting dimension to look for, right? So that we can do these tasks with a better accuracy, with a more promising generalizability, right? Because explainability or generalizability form the fundamentals when if at all we want to run these models in the real time, right? So we should be in a position to tell confidently that look, this model is going to handle these many variations or these many varieties that you can think about. It can handle it and it can perform the task at hand, right? So thinking specific to the problem at hand, specific to the modality at hand, I believe is going to, I mean, is the key to solve the problems with a good amount of accuracy and with some intuition, right? So it should not be that so it's nothing that we kept a model and we got accuracy. No, if we can tell or if we can sense something intuitively and we experiment with some intuition, and of course if we see the results with the similar intuition and if we can explain that back and forth is going to be an interesting way, I would say, to look at problem solving and designing new methods or coming up with new workflows, right? So thanks for your kind attention, and so that's all I have. And so if you are interested, I think you can read this paper. I mean, most of the material I copy pasted from the paper itself, and the paper has even more details which I might have missed during this 40 or 45-minute presentation. Right? Yeah, yeah. Thank you. If any other questions, I can take some of them.
Yeah, thank you so much, Dr. Naveen, for sharing your expertise with us. Thank you so much. So participants, if you are having any query, you can write in the chat box.
Okay, so I can read some of them. In the context of MRI lesion segmentation using deep learning, how can one effectively address inter-center variability and the scanner-related heterogeneity during the initial stages of dataset preparation to ensure model robustness and generalization, right? So, very good question. So this, so one thing I can talk about. So I believe you might be talking specific to some of the imaging, I mean, like imaging styles in MR. So I'm not sure if you're talking from T1 imaging perspective or T2 imaging perspective or a flare imaging perspective. So one thing what you can do is like there is something called as Fourier domain adaptation. So it is a celebrated paper in computer vision. So wherein they try to segment natural objects in a city scene. Say, for example, you trained a deep model to segment out cars, trees, or some human beings and some buildings on a given road in Indian scenario. So now, if you want to apply the same model in, for example, in a European scenario, so this is not going to work, right? So what they do is like, so they prepare their data using something called as a Fourier domain spectrum transfer. So wherein they try to make the Indian scene look like in a European style, right? So the visuals, correct? So the contrast or the brightness or the pixel intensities or the style that we see. So they transfer their data and they train their models on the transformed data, right? So that that model is trying to segment the objects in an Indian scenario, but in a European style, right? So this is a very good paper, and it's called as Fourier domain adaptation. You can just search for it; it will appear in an archive link in the first URL in the Google. And a similar style you can apply. You can try to bring in that kind of a context into the picture, and you can see how well you can segment the anatomy or the lesion of your interest for the task at hand. Right? So again, so this is one idea that popped up my mind, but there are several other existing methods also might be there for the same question what you might ask. But if you want to do something on the from the map perspective or from the style transfer perspective, you should definitely look for something called Fourier domain adaptation. And I can confidently say, so that paper has been the foundation for so many other domain adaptation models in the context of medical image segmentation. Okay. The second question, what are the most effective strategies for augmenting and expanding MRI datasets to improve the performance and generalization of deep learning models in medical imaging tasks in terms of DWI and T1 weighted imaging? So one thing is like the synthetic data and generative AI, right? So I hope you are quite familiar with these terms. So what you can do is like you can sample or you can train some models like diffusion models or some GAN like architectures. Of course, diffusion models are doing good compared to the generative adversarial networks. So that is one way to improve or bring in some sort of diversity into your data. And the other way is like depending on the task. Excuse me. So depending on the task that you are trying to solve, right? You mentioned it as segmentation task, right? So what you are segmenting, is it an anatomy you are segmenting, or is it a lesion that you are segmenting? So if it is a lesion that you are trying to segment, so usually data sets with lesions are quite limited, right? So compared to the data sets without lesions. So what you can do is that you can use these synthetic models, I mean, diffusion models to synthesize MR images with different lesions, so that you are trying to bring in some balance between the healthy MR scans versus the MR scans with lesions, right? So that is one way to look for where you are trying to bring in a good amount of class balance between the healthy scans versus scans with these lesions and all, and then you can really look for other adaptation strategies like for the previous comment which I have answered, right? So you can also think about along with the synthetic data and all, you can also think about other regularization or generalizability aspects that you can bring into the picture. So while working on multi-class image classification, can the output be termed as a prediction? Is it appropriate to call it that way? And rather than indigenously perform segmentation, is it more efficiently done by deep learning models internally in certain classes? So I'll see this has two different questions. So multi-class image classification can be called it as a prediction. I mean, it is a generic term wherein we are saying where. So what do you call it, right? So given an image, the model gave an output something. So the model has predicted that this image is coming from CNV or this image is coming from DNV. And that's a generic term to I mean, to give some explanation to the overall workflow that I was trying to talk about. Of course, yeah, you can call it as a model prediction, right? So that is what we often refer to. Is it more efficiently done by deep learning models internally in certain classes? Did not follow the question what you are trying to ask. So maybe in the meantime, I'll go to the next question. Which transformation to apply in the Fourier domain, amplitude, phase, or both when dealing with specifically with medical image segmentation? And is there a potential to combine Fourier domain adaptation with multimodal learning for cross-modal segmentation? This is a very good question that you have brought up. So it's always going to be so phase. If you look at it, so phase actually preserves the structure, right? So people usually fuse the amplitude; they retain the phase, correct? So even the Fourier domain adaptation paper, if you go back and look at it, so they retain the phase and they fuse the amplitude.
ये क्या है कि आपका पीपीटी अगर थोड़ा सा शेयर कर देंगे काट वाट के 2 4 5 सकता है बस नाउ
there any potential for combining Fourier domain adaptation with multimodal learning for cross-modality? Yes, I believe there are definitely papers. I mean, recently I haven't read them in this particular context, but yes, there are some papers which actually do this. For medical image segmentation tasks involving small datasets, several class imbalance and inter-center variability, which class functions are most effective in improving model performance and ensuring robust lesson description. Right, so handling class imbalance, right? So there are some weighted form of loss functions. So, for example, if it is a classification task, people will do weighted cross entropy. In some papers, they have experimented with the focal loss and all. And there are techniques to how do you train your model, right? So this these days the data loaders either in TensorFlow or in PyTorch, they come up with some sampling mechanisms. So wherein in the given mini batch, right? So an epoch consists of several mini batches. So they try to ensure that in every mini batch there are samples coming from a minority class. So they typically oversample, they overrepresent the data points from a minority class so that the model gets to look at the minority class more compared to the majority class, right? So there are good amount of what is a clever samplers that will enable your data loader in a way that you can forward pass the minority class samples in a more efficient way. And the second, and so this was the second thing. The first thing was weighted loss functions. Second one was sampling, and the third one is the synthetic data, right? So if you can generate or if you can simulate some synthetic images of the minority class using diffusion models and all, so that is one way to handle it. And the other way is having a pre-trained self-supervised tasks, right? So self-supervision is a kind of a good initializer wherein you can do some self-supervised task on a given set of data points and then you fine tune your final task. For example, if it is a classified task, you fine tune your classified model from the pre-trained weights of the self-supervised network, right? So that is one way to look at it. But these 4 or 5 methods, what I have discussed till now, they were quite popular in the previous year by this time. But right now, I think so many other methods might have come up. But you should definitely you can start from these techniques what I have just mentioned. But there can be other advancements which might have happened already. How to come up with novel loss function for the classification task? What intuition helps one to decide on introducing the novelty in the function, right? So this comes from what problem you are trying to solve, right? So again, novelty itself has a different perspective. I mean, like different people have different opinion on what we can call as novel. So I would say, like, how can we design or bring in some loss function which can help the task at hand that we are trying to solve. Right? So you think more about the problem, right? So these days, I mean, we we do not, at least what I have seen is that when a given a task, we quickly jump on to solve it, right? So because of the availability of several resources, Google Colab is giving you the compute, PyTorch, TensorFlow, they have inbuilt functions to write the data loaders, do the forward inference, backpropagate, update the model, and give you the inference and bring down those diagrams of loss curves or some class activation maps and all, right? So if we can spend some good amount of time on the data that we are trying to process or analyze, that can give you some intuition about it, and then accordingly you can choose, right? So the novelty, or what do you call, the contribution that we might be doing, but it need not be always on bringing a novel loss function or a novel architecture, right? So it can be from the data perspective also. So can you come up with a nice transformation in such a way that whatever data is coming from different data centers, you are projecting it onto a common platform, and then you are training excuse me, and then you are training an existing model on this particular projected data, right? So this way you can think about other things. So what I can tell you is, like, think about the data more, and then rest the model, the loss functions. I mean, they can be secondary because there are so many tools which can automate these things. First, think about the data, like what exactly you're solving and what else you can think about in and around it, right? So we often jump onto solving the problem first before understanding the data. So data also should be given equal amount of importance is what I want to convey. So that will give you more ideas, right? It need not be always from the architecture perspective. It can be from the data perspective as well. Yeah. So these are the questions I can see on the task. If you have any other questions, so please feel free to reach out to my email ID, and maybe Professor Deepak, I can share the slides. I think that is what you are mentioning. So I will definitely send out along with the URL of the paper and session PPT slides as well. You can share it. Yeah.
Yes, so that participants can go through, and if they're having any other queries, they can directly drop an email.
Email, yeah. They can email me, and I'll be happy to.
Yeah, so we could see the feedback from the participants that they have really enjoyed your session. So
Okay. Yeah.
and they might have got a lot of interesting ideas, because OCT is really difficult to understand, right? It's fundus image is a bit easy to understand because somewhat similar
Right. Yeah.
to the structure of the eye.
Correct. Yeah.
So
Yeah.
it's very difficult. So I mean, we have beautifully explained the principle behind OCT.
Yeah.
And also you have talked about one interesting method which you have developed. So probably you've also talked about some of the limitations, future research directions. So I hope you have any participants might have got some idea. So thank you so much for joining us and sharing your expertise, your thoughts, your insights, right?